Hi friends, welcome to distributed computing system. Now we will discuss regarding a logical time and logical clocks. From the point of view of any single process, events are ordered uniquely by times shown on the local clock. Local clock represents whenever a process occurs in any computer in a single process, the clock occurred at that situation, or say at that system. We cannot synchronize the clock perfectly across a distributed system. We cannot in general use a physical time to find out the order of any arbitrary pair of events occurred within it. Synchronization is very important in a distributed computing system. If a local time or say physical time occurred at an individual computer cannot be used to synchronize the clocks existed in a different computer, because we know it physical time or a local time of each individual computer is different. We can use a scheme that is similar to the physical causality, but that applies in a distributed systems to order some of the events that occurred at different processes. This ordering is based on two simple and intuitively obvious points. So the ordering or the synchronization can be done in a distributed system by using a logical time and logical clocks here. The 2 points are important here. One is if two events occurred at the same process Pi, then they occurred in an order in which Pi observed them. This is the order that we define above. Means if events occurs in a process Pi, in the sense that in any process considering in any computer, the events occurs there. Events represent the actions or the work carried there. Then ordering is maintained in a Pi. That order, whatever the process considering it will be considered there. Let me consider one example. E1 and E2 are the two events occurred at the process P1, right? Then E1 occurred first, or say happened before the E2. That's the order maintained in a process Pi. The next point, whenever a message is sent between the processes, the event of sending the message occurred before the event of receiving the messages. Considering it to process P1 and P2, from the P1 you are sending the message to the P2. Then at that instance, P1 should occur before the P2, or say event in the P1, E1 in the P1 should occur before, or say first, later on E2 in the P2. When the message is sent from P1 to the P2, or from one computer to the other computer, or the processes existed in a single computer. Lamport called the partial ordering obtained by generalizing these two relationships happened before relation. Happened before relation is very important here. It is also sometimes known as a causal ordering or a potential causal ordering. We can define the happen before relations by the Lamport in the three different ways. HB1 happen before 1 represent if the process Pi, if you are considering a single process Pi, then at the time E happened before of the E dash. Clear? E happened before of the E dash, then E tends to E dash. Second one means in the first single process, if the two events happens, then what is the first event happen? E, later E dash happens there. Then where we are maintaining the ordering or the synchronization in the process. Happened before 2, the second rule represent message M. You are sending a send message M to the receive message M. Represent in a process P1 you are sending a message, in a process P2 you are receiving that message. Where send M is the event of the sending the message and receive is event of the receiving it. Means send M should happens first, or say happened before of that of the receive M. It's the second rule. Second rule represents the message sending from one process to the other process. Happened before 3 rules. If E dash, E double dash, the 3 events occurs there. Either they may occur in a single process or in a different process. Then the rule says that E tends to E dash, in the sense that E happened before of a E dash E dash happened before of the E double dash, then obviously the E happened before of the E double dash. And this is some more theory regarding this. If E and E dash are the event, and if E happened before of the E dash, then we can find the series of events E1, E2, En occurring at one or more process such that E happened before of E1 or and E dash happened before of the En, and for of I is equal to 1 to n minus 1. Either HP1 or HP2 applies for the EI and EI plus 1. Then logical clocks represents here. Lamport invented a simple mechanism by which the happened before ordering can be captured numerically, called as a logical clock. A Lamport logical clock is a monotonically increasing a software counter whose value need bear no particular relationship to any physical clock. Each process PI keeps its own logical clock Li, which it uses applies so-called Lamport timestamps to events. What do you mean by logical clock represents? In a process PI, a software is maintained which is incrementing its value by 1 when a time goes. That timing is maintained in each process or with each events occurred in the process. That is a logical clock. This is some of the logical clocks happens here. In the rule says we are considering a LC1 logical clock. 1 represent here. Li tends to Li plus 1 represent there in the process. The logical clock is incrementing its value by 1, means a counter is set there in the process which is incrementing its value by 1 at each second, we can say. When a process PI sends a message M, its pick back on a M the values of a T is equal to Li, right? And second point is that on receiving a M comma of T, a process Pj computes a Lj is equal to maximum of Lj comma T, and then applies a LC1 before timestamps the events received at a M. Represent M whenever you are sending from a one process to the other process. In the other process, it will take out the time on receiving a M comma T. There it will compare the timestamps of a previous one and a present one, which is a maximum one. It will consider that as an updated value, and that will be received in the M. Thanks for watching.